So I've got two vectors here. It's like the one on the left over here, this red one. Just for the sake of having something to call it, let's call this vector A. So the capital A and the little symbol over the top denotes that A is a vector, not a scalar. And then over here we have vector B. So these vectors could, for example, be position or displacement vectors, with each box representing 1 meter. So vector A moves to the right 1, 2, 3 meters, and then down 1, 2 meters. Whereas vector B moves to the left 1 meter, then up 1, 2, 3, 4, 5 meters. But your trip hiking, for example, might not always be made up of just one vector of motion. For example, you might first move along vector A, and then maybe next you want to move along the direction of vector B. So to figure out what this is, what we need to find is known as the vector sum, A plus B. And first, let's handle this graphically. So we're going to zoom out a little bit, come over here so we have a little bit of space to work, and we're going to find out how to find A plus B graphically. To add these two vectors graphically, the first thing we're going to need is a starting point. Now you don't have to pick the origin, but the origin is a pretty easy starting point to have. And then from there, the first thing we're going to do is vector A, because that's the first term in our sum we see over here. First we do vector A, then we do vector B. So from our starting point, vector A goes 3 to the right and 2 down. So there we have our vector A. So now we want to add in our vector B here. And B, this time, since we're trying to do A plus B, our new starting point for vector B is right here at the tip of vector A. So from the tip of vector A, we now do exactly what B does, which is 1 to the left and 5 up. So it would look something a lot like this. And so now we've arrived out here at our end point. So the question that this vector sum answers is, how far did we go from where we started to where we ended? Forgot to label vector B here. There we go. And so to figure out how far we went from the start to the end, let me grab a third color here. We just draw a vector that begins at our starting point and ends at our ending point. And this is our vector A plus B. You can see that if you travel along vector A, so vector A, 3 to the right and 2 down, here we go 3 to the right and 2 down over here, and then from there we travel along the path of vector B, 1 left and 5 up, we are left with vector A plus B, which itself goes 2 to the right and 3 up. So what this resultant vector is saying in terms of our hike is, first we went 3 meters east and 2 meters south, then we went 1 meter west and 5 meters north. So how far are we from where we started? We are 2 meters to the east and 3 meters north of where we started. But this is far from the only way that we can add vectors. There's also something called unit vector notation. where, for example, since we know A is 3 to the right and 2 down, we can write A as 3, and then to the right, we denote to the right as I hat. I hat is the unit vector in the x direction, so positive 3 in the x direction, and then we're going negative 2 in the y direction, and the y direction is denoted with j hat. And we can do this same thing for vector b. B is negative 1 I hat plus 5 j hat. And from here, adding the vectors is a fairly straightforward process. You can just kind of draw a big line across and add them up, and we're going to add the like terms. So first, we're going to add our I hat terms, and what we have here is we have 3 I hat on the top and negative 1 I hat on the bottom. So when you combine those together, you get positive 2 I hat. Then we can look at the y components or the j hat components. We have negative 2 on the top. Don't forget the negative sign. Positive 5 on the bottom. So negative 2 plus 5 is positive 3 j hat. And so this right here that we've just found is the same thing. It's vector A plus vector B, or the vector sum of the two of them. And if you notice, this is the same result that we got graphically. These are just two different ways to show the same thing. If we add them graphically, we see A plus B is 2 to the right and 3 up from the overall start to the overall end. And doing the math in unit vector notation, we see the same thing. 2 to the right, represented by 2 I hat, and 3 up, represented by 3 j hat. So there's one more way that may be helpful to know, something that can help you add vectors, and let me just get myself a little space right here. You can also represent these vectors using what we call column vector notation, where instead of writing out A as 3 I hat minus 2 j hat, or instead of showing A as this arrow up here, we can write A like this, as a matrix with 2 elements, with a 3 and a minus 2. So in this notation, the top number always represents the x, or the I hat component, and the bottom number always represents the y, or the j hat component. We can do the same thing for B. As I'm sure you've guessed, B will be negative 1 up top, 5 on the bottom. And then from there, to add the 2, all we need to do is take our 3, negative 2, and add to that our negative 1, 5, and get. So what we're doing here is adding the top numbers together. So we'll be adding this 3 and this negative 1 together to get our new x component of our resultant vector, which is 2, the same as it was when we found it the graphical way, and the same as it was when we found it adding the vectors with the I hats and j hats. And for the y component, we add the negative 2 and the 5 again to get positive 3. So some people like this notation. We once again get A plus B is 2 to the right and 3 up, the same all 3 ways. But some people find this to be a more compact and easy way to write it like this with all of the column vectors than to carry around all of these I hats and j hats, because sometimes you can forget to group like terms. But all of these are ultimately the same thing. You're adding 2 vectors to find the resultant vector. The resultant vector that takes you from where you started to where you ended, with multiple steps in between but your resultant is just worried about where you started and where you ended, not anywhere where you went in between. Again, we didn't have to start at the origin. We could have easily started somewhere else, and we would have obtained the same result, because it doesn't matter where on the grid our vectors are. All that matters is what direction they're pointing and how big they are.